Hi everyone, today we'll continue with derivatives, and today we'll talk about the derivatives of inverse functions. So before we start to do the differentiation, let me revise what is inverse function. Or before we even talk about inverse function, what are functions? Okay, so as you know, function is that like if you have like from A, you have the number, maybe a 1, then to B, you have number 2, okay? From 1 to 2, you map 1 to 2 from A to B, you undergo a function f. Which means if that is the function f, then the inverse of it will map, the inverse of that function will map 2 back to 1, right? So this is the concept of inverse function. Okay, so if you read the definition, suppose that f is 1-to-1 function. Okay, why is it so important that the function has to be 1-to-1? Because if you remember, in order for a relation to be a function, it is either 1-to-1 or many-to-1, right? Many to 1, which means one input can only have one output, but the output can be the same for a different input. This is the definition for functions. However, only 1-to-1 function can have inverse function. Why? Okay, maybe I should draw to you. For example, a very simple example. Okay, from 1 you map to maybe a 2, then from 2 you map to a 4 with function f. So function f is actually a 1-to-1 function, right? 1-to-1 is a function, no problem. What about the inverse? From 2 back to 1, from 4 back to 2. The inverse of it is still 1-to-1. So both of them are functions. However, if it is many-to-1, 1, 2 maps to 0. Okay? Like this. F. In fact, f of x, you know that this one should be x to the power 0. Okay? So, this relation here is a many-to-1 function. It's a many-to-1 relation, which is a function, no problem. Okay? Because one input only have one output. However, f inverse of it, if that exists, no, it doesn't exist. You see? F inverse, if you really want, it is actually a one-to-many. One-to-many relation is not a function. Hence, only one-to-one relation, only one-to-one function can have inverse functions. Alright? And this is very important because later on when we talk about the inverse of trigonometric function, we need to restrict the domain to make it injective. Or it is actually, it means one-to-one. We need to make it injective. Okay, we'll talk about it later when we talk about the domain and range for inverse trigonometric functions. So let's go through very quickly. What are the steps? Okay, the steps to find the inverse function. Find f inverse. So suppose we have a very simple function, f of x equals to x cubed. You realize I didn't take x squared because x squared is not injective. Alright? What you usually do, the traditional way is you let f inverse of x, f inverse of x be y, so that f of y is x, right? Then this is equation 1. Equation 2, you go replace your x with y. This is equation 2. Equation 1 sub into equation 2, x equals to y cubed. What do we want? We want y. So y equals to the cube root of x. Hence the f inverse of x is cube root of x. This is what we do traditionally. Or if you know the shortcut, or you can also do it like this. Initially it is y equals to x cubed, right? Y equals to x cubed. You go switch your x and y. Okay? Means instead of y here I put x, instead of x here I put a y. So x equals to y cubed is what we have now. I still want my y. So y equals to cube root of x. Hence f inverse of x equals to cube root of x. Okay? So these are the steps to find f inverse if you forget. Alright, then the next thing I want to talk about is, maybe we should revise on this one, the properties of inverse function. So number one, I told you that the original function has to be injective, okay? Have to be injective in order for the inverse to be defined as a function. Then secondly, you need to know that the graph of y equals to fx, and its inverse, y equals to f inverse of x, is symmetrical about the line y equals to x. Why? Because if you put in maybe a, you get a b. This is for f, okay? If you want to graph f inverse, you put in b, you get an a, which means it is symmetrical about this y equals to x. So these are graphical properties of inverse functions if you want to graph it. Then thirdly, this is a very important one, which is if you put the inverse back into the function, you'll get back you'll get back your input. Maybe I should put it like this. Y equal to fx. If we have suppose we have a y equals to fx, okay, then we know that f inverse of y will get x, right? Then now, what happens if I substitute in this y? This fx is y, right? I put it here. What do I get? I get f inverse f of x is x. Similarly, if I put this x back into this equation, y equals to f of f inverse of y. So two of them are actually interchangeable. You can change this one to x as well. Okay, so these are very important properties that you will use later. Okay, then now we'll start with the derivatives of inverse function. So one look at the theorem and say, oh my god, so complicated. F inverse prime, then got b1 over f prime, this one. Actually, don't worry. This one means you find the value of inverse, f inverse of b, then you put it into the derivatives of f. If you want to look at this formula, it just means you differentiate f inverse with respect to x at x equals to b is equals to the reciprocal of the derivatives of f with respect to x at x equals to f inverse of b. I know it's still very you still very complicated, but never mind. Let's go through. Maybe we should prove it so that you can remember it better. Alright? So again, we'll start with the two properties that we discovered earlier, which is these two. F of f inverse of x is going to give you x, and f inverse of f of x is going to give you x. And we only need one of them actually. So maybe we choose the first one. Alright? So what I will do here is I differentiate both sides with respect to f inverse of x. Be very careful with the notation because prime and inverse are different things, okay? dx of x. So actually, if you look at this is actually a composite function, right? A function inside another function. And if you see composite function in differentiation, the first thing that comes to your mind should be chain rule. It's raining here. Okay, never mind. So for chain rule, differentiate outside function, you differentiate f, you get f prime. Copy whatever you have inside. Differentiate inside function. But we don't know what is the derivatives for f inverse. Just write dx of f inverse of x. And actually this is what we want, right? This is actually what we want. What about right hand side? You differentiate x with respect to x. Get a 1. And I told you this is what we want. So just move around thing. 1 over f prime f inverse of x. And that's it. And if you want to write this in like prime kind of notation, you just write this one. Equals to 1 over f prime f inverse of x. And this is it. Very simple proof to this one. Okay, so the derivatives of inverse function is 1 over f prime, then you put in the value of f inverse of x at that particular x value. Okay, end of proof. Okay, now we'll do a very simple exercise. Okay, so we need to evaluate df dx at this point and this one at a to show that actually you know what, we are just proving this one. Actually we are proving this one, but with specific functions and values. Alright, so what we need to do here is actually, number one, we need to find f inverse of x. Number two, we need to find df dx at x equals to f inverse of a, and df inverse dx at x equals to a. They will go and compare these two values. Okay, actually it's compare the reciprocal of this one with this value, whether they are the same. Okay, let's start very quickly. So the first one is very easy. Like I said, whenever you need to find the inverse function, the shortcut way is you switch your y and x. So now instead of y equals to 2x plus 3, write x equals to 2y plus 3. Then you solve for y in terms of x. Okay, maybe I should write like this: f inverse of x, half x minus 3 over 2. Okay, then next thing is df dx. Okay, df dx, which is just a 2. So no matter what value it is, your df dx at x equals to, okay, f inverse of -1 is what? Actually it doesn't matter lah, but just for the sake of writing it, it's -2. Okay, -2 is equals to 2. Okay, can remember this value, and I will expect to get a 1 over 2 later. Now we differentiate this f inverse. We just get a half. So df dx at x equals to -1 is also half. Then you know that 1 over 2 is half. End of proof. Okay, so yeah, that's it. Number 2, okay, we need a quotient rule, but before that, let's find the inverse function first. Like I said, switch your x and y, express y in terms of x, y equals to x minus 2 over 1 plus x. So this is your f inverse. This is actually your f inverse of x. Next, differentiate df dx. Oh, this one is quotient rule, so you know that you need to do like this. Bottom function, differentiate top minus copy top, differentiate bottom square. Okay, 1 minus x, minus become plus, x plus 2, 1 minus x square, 3 over 1 minus x squared. And now we want to find df dx at x equals to, okay, I'm running out of space here. F inverse of half is what? Half minus 2 over 1 plus half times 2 times 2, 1 minus 4, -3. Am I right? X minus 2, oh, then this one 2 plus 1 is, so it's -1, and is it negative 1, right? Equals to, you put in negative 1, 3 over 1 minus 1, which is 2 square, 3 over 4. Okay. Then you compare it with the next value. Okay, the next one we need to differentiate this one. So f inverse x is x minus 2 over 1 plus x. Okay, so we just differentiate f inverse prime x, or if you like, you write df inverse dx, copy, differentiate, square. Okay, 1 plus x minus x plus 2, 1 plus x square. This and that can cancel. 3 over 1 plus x square. Then df inverse dx at x equals to a. Who's your a? Half. Is 3 over 1 plus half square. 3 over 3 over 2. 3 over 9 over 4. It is 4 over 3. Okay. Then this 4 over 3 compared to the reciprocal of 3 over 4. They are the same, right? Okay, end of proof. That's it. So it's actually very simple as long as you know how to do. Okay, then next one. So first thing, find your f inverse. Switch x and y. Y in terms of x. Do you realize that I only take the positive version? Why? Because the question actually restricts the domain so that it is injective and it has an inverse function. Okay, so f inverse, but I don't like to write like this. Later when you want to differentiate, you better write like this. It's easier for you to differentiate later. Anyway, differentiate, bring down the power minus 1. Okay, then we need to find this value. F inverse of 5 is 5 over 2 to the power half. Okay, so df dx at x equals to the square root of 5 over 2 is 4 times this one, 5 over 2, which is actually 2 sec 10, right? 2 sec 10. Okay, so remember this value. Next, we differentiate the inverse function. We differentiate this one, bring down the power minus 1. Wait, sorry. Okay, copy the wrong thing. Power minus 1. Differentiate inside function. So it's 1 over 4 square root half x. So if we substitute in x equals to 5, it will be 1 over 4 square root 5 over 2, which you know the answer, like this is 1 over 2 sec 10. So 1 over 2 sec 10 is equals to the reciprocal of 2 sec 10. End of proof. Okay, so it's actually very simple as long as you know the concept, as long as you know what is the formula talking about, as long as you know what is inverse function and its relationship, the properties with its original function. Alright? The next thing we'll talk about is, okay, now we'll talk about the inverse trigonometric functions, which I think you should be very familiar with. The sine -1, cos -1, tangent -1 on your calculators. Okay, so in order to understand what is inverse trigonometric functions, you need to know this inverse function is no longer talking about the ratio of maybe hypotenuse to opposite, opposite to hypotenuse, adjacent to hypotenuse. We no longer talk about the ratio of those things. But instead, for inverse trigonometric functions, we are actually talking about the arc. Okay, if you remember what is arc from your circular measure. Okay, so yeah, let's look at this arc. Okay, this arc, the one in blue here, the one I highlight in yellow. So if I draw it here, okay, the arc is the one that in blue color, right? This is the arc. Okay, then you draw a 90 degrees. Then this one, maybe you call it theta. Okay, and you know that this is a unit circle. Unit circle means the radius here is equals to 1, and this is equals to, from here to here is x. So by your trigonometry, you know that cos theta is equals to x. Okay, and now like I said, we are talking about the arc. Okay, so if you remember your arc length formula, s equals to r theta, and in this case your r equals to 1, so s equals to theta. Equation 1, equation 2. Okay, because we want to find the relationship between this s and cos and the trigonometric functions of that theta, we'll substitute equation 1 into equation 2. Okay, 1 into 2, cos s equals to x. What does it mean? Remember, cos is a function here, and cos, I will talk about the restricting domain later. Cos is a function, means we can restrict domain to give it a inverse function, remember? And let me remind you that f of f inverse of x is going to give you back your x. F inverse of f of x is going to give you x. Okay, so now for this equation here, I will take cos inverse on both sides. Cos s equals to cos inverse of x. Inverse of x. So by this one, is it this one? No, by the second this and that can cancel, right? So s equals to cos inverse of x. And what is this s? This s is the arc whose cosine is x. In short, we call it arccos of x. And this is the inverse cosine functions. Okay, so similarly, if you want to show that you want to understand what is inverse sine, you just have to look at this arc here. Okay, you should be able to show that arcsine is equals to cosine. Arcsine is equals to sine inverse. Okay, but all of this is not important. Okay, the most important thing for inverse trigonometric function is the range and domain of this inverse trig function. Let me go to a new page. Okay, range and domain. Okay, so we will start with the first one, which is inverse x. Okay, y equals to arcsine of x. Okay, this means x equals to sine y, right? So like I said earlier, in order for a trigonometric function to have a defined inverse function, it has to be 1-to-1. Because we know that trigonometric function is periodic, like it is actually like this, right? Continue. So if we reflect it on y equals to x without restricting the domain, it will be something like this, right? Like this, which is a one-to-many function, which we don't want. Okay, so we need to restrict the domain. So for sine, it's actually we'll just take this part to this part. And I want to tell you why later. And actually, I'll tell you why now. If you remember, all science teacher crazy, you know that sine is positive at the first and second quadrant. Meaning we cannot, if we want to take first quadrant, we cannot take second quadrant. If we want to tag fourth quadrant, we cannot tag the third quadrant. Alright? So in order for it to be injective, we can only tag one quadrant of the same sign. There is another condition that we want it to be, which is we want it to be continuous. Okay, we want it to be continuous. If it is not continuous, means what? We cannot differentiate, right? Remember the differentiability, that we have 5 conditions that cannot be differentiated. Okay, so meaning if I tag this part here for positive and suddenly I tag this part for negative, it is discontinuous already, right? Discontinuous at x equals to 0. So I have no choice but to tag from here, maybe I should use blue color, from here to here, right? Which is the first quadrant and the negative first quadrant, which is the fourth quadrant. Hence the domain will be -1 to 1, right? And the range will be from -pi/2 to pi/2. Okay? So this is for inverse sine. So if you want to compute the value of sine inverse of half is equals to just pi/6. Only pi/6, not like when you are doing your solving your trigonometric equation, you will have one answer from quadrant 1, another answer from quadrant 2. But in this case, when we are talking about inverse trigonometric functions, it can only have one answer. Okay? So what if it is negative? Because it can be in between -1 and 1, right? Negative half. So automatically, you know that the answer is fourth from quadrant fourth quadrant. Or if you like, you can write -pi/6. They're actually the same thing. Okay, so this is for inverse sine, and we'll go through inverse cos and tangent very quickly. Okay, y equals to arccos of x means x equals to cos y, right? So remember, all science teacher crazy, positive, negative, negative, positive for cos. Like I said, it has to be injective, means we only choose one for positive. It has to be continuous. Hence, we'll choose quadrant 1 and quadrant 2. So the domain is still -1 to 1. The range is 0 to pi. Meaning, if it is cos inverse of 1 over sec 2, 1 over sec 2, it is quadrant 1. If it is negative, means it is from quadrant 2. Okay. Then for tangent is the same as, not exactly the same. It's similar to your sine. Okay. Because the sign are the same, right? For tangent is positive, negative, positive, negative. Injective, continuous. The domain you have to be very careful, because if you remember the graph of tangent, it is like something like this, right? Then so actually, you know that the range of f is the domain of f inverse. Hence, the domain for tangent inverse will be -infinity to infinity. Not include. Of course, when you write infinity, you never include one. But the range, like I said, quadrant 1 and quadrant 4, or quadrant 1 and negative quadrant 1. Negative pi/4, that's right, pi/2. Not include, for tangent not include, because at pi/2 or negative pi/2, it is actually undefined. Okay, pi/2. Okay, so similarly, tangent inverse of sec 3 is pi/3, 60 degrees. Arctangent of negative sec 3 is either negative pi/3 or 5 pi/3. Okay. Then the rest are very easy lah. The rest, if you know, cosecant theta is 1 over sine theta, right? So sine inverse x over y will be cosecant inverse y over x. Secant theta is 1 over cos theta. So cos inverse x over y will be secant inverse y over x. Cotangent theta is 1 over tan theta. So tangent inverse x over y is cotangent inverse y over x. And for two of them, cosecant and secant, the range and domain is exactly the same as sine and theta, except for cotangent is different. Okay, I put a note for you. For y equals to arccotangent x, the domain is still negative infinity to infinity, but the range is 0 to pi. Why? You still have to refer to the graph of cotangent. It is actually like this, right? Then you say, hey, if you want it to be injective, then the positive version we just take this one. No? Negative, why don't we take this one? So that it is from negative pi over 2 to pi over 2. But the problem is, it is discontinuous at x equals to 0. So in order for it to be continuous, we need to take from, the best choice is to take from 0 to pi. Of course, not inclusive of 0 and pi. So that it is differentiable throughout the domain. Okay, so this is the range and domains for inverse trigonometric functions. Okay. Then the next one is inverse hyperbolic function. You know that the hyperbolic function is defined with exponent, right? Let me see if I have, yeah, it's exponent here. So you expect the inverse of it to be defined in terms of ln. Okay, I'm not going to prove all of them here, just for your information, you have this table. Okay, hyperbolic inverse is defined by ln. And of course, you have the differentiation table for inverse trigonometric function and inverse hyperbolic functions. But do you find it very weird that how come you differentiate sine inverse? You suddenly get 1 over square root of something. Like, because you know that you differentiate sine, you get a cos, you differentiate cos, you get negative sine. How come when you talk about the inverse function, the derivatives of inverse function, all of the trigonometry disappear? It is actually from the theorem from earlier. This one. It's actually from here. Okay. Maybe we should just prove one of it. Okay. I'm going to show you the first one. I'll show you this one. Okay. So f of x equals to sine x. Okay. Then in order to use that theorem, we need what? We need to find f inverse of x, right? And we know that f inverse of x is just sine inverse, which is arcsine of x. Am I right? Then what is the derivatives for sine x? Cos x. Am I right? Then from the theorem from earlier, and we also proved that theorem, this one, 1 over f prime f inverse of x. Okay, so f prime x is f inverse prime of x is 1 over f prime f inverse of x. Meaning the derivatives for sine inverse of x is equal to 1 over, it's a chain rule, remember? Differentiate sine, you get a cos. They will put in sine inverse. But you might ask, what the heck is this? Why suddenly got cos and inside got the sine inverse? You need to make everything into the same function. And the easiest way to convert a cos to a sine is use identity. Cos square A plus sine square A equals to 1. And the reason why I choose this identity is because later on I will have a square root of something, right? And in order to have a square root, I need a square. And you know that cos A is just square root of 1 minus sine square A. So now you just plug this into your A here. So your A here. Okay, your A here. So you have the derivatives for sine inverse of x. 1 over cos, no more cos, square root of 1 minus sine square. I think I better write like this, arcsine of x. If not, you're confused that, oh, maybe sine inverse of x means 1 over sine x. No, it's different. This is cosecant, you know. Okay? And now what? Remember the properties from earlier? F of f inverse of x is going to give you your x. So this fella here, what is this fella here? This actually sine, you don't care about the square first, of arcsine of, okay, not arcsine, okay. For here I think I write like this better. Square, right? So what is this? X squared. Hence, it will just be 1 over square root of 1 minus x squared. Finish. You see how amazing it is. You differentiate the sine inverse, then the sine and cos, everything disappear. Just come back to x. So if you are interested, you can go ahead and prove all of them. Okay, just show you that the concept is this. The concept, you are using the derivatives rule for inverse functions. Right? Okay, time to differentiate. But before we do the differentiation, let's look at the table, see what we have here. Okay, so we have the derivatives for inverse trig and inverse hyperbolic. And actually, you know what? You don't actually need to struggle to memorize all of them. If you really want to memorize, you only need to memorize half of them. And I will show you how I remember. Okay, so let's look at inverse trig first. Inverse trig, you just remember sine, tangent, and secant, they are all positive. Okay? Sine, tangent, secant, they are all positive. Cos, cotangent, cosecant, they are all negative. The one that start with C are all negative. Sounds very familiar, right? This is exactly the same logic as your trigonometric functions. Alright? Then there are 3 patterns that you need to remember. The first one is with square root. Okay, with square root, start with 1 and minus. And you know who I'm talking about. I'm talking about the sine inverse. 1 over, you see, with square root, start with 1 and it is start with 1 and minus. Okay, with square root, start with 1 and it's minus. Then for tangent hyperbolic, tangent inverse, without square root, you see, no square root there, right? Also start with 1, but this time it's plus. And actually doesn't matter whether it start with 1 or x squared, because it is plus, it doesn't matter. Then for secant, with square root and with x outside, start with x squared. Instead of 1 minus x squared, it is x squared minus 1. Okay, and it is minus 1. So this is how I remember, just a few patterns that you need to remember. Whether it got square root or not, whether it is plus, minus, whether it start from 1 or x squared. Okay, inverse trigonometric functions. Then for inverse hyperbolic function, you have to be very careful because it is very similar and the sign are different. Okay, so for sine, cos, and tangent, the first 3 are positive. Secant, hyperbolic, cotangent, cosecant are negative, just like your normal hyperbolic without inverse. Then the sign is different. For sine is negative, for sine is positive. Then this one is still negative, 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 positive. Okay, just be very careful with the sine. Okay, we'll do the exercise now. Number 1, arccos of x squared. This is actually very easy. Just don't forget to do your chain rule, okay? So dy dx, remember, cos is negative, right? Negative 1 over square root of 1 comes first, minus square whatever inside, then chain rule, multiply with the derivatives of x squared, so it is 2x. Finish. Okay, just like that. Number 2, oh, for this one, okay, never mind, just do first, okay? Dy dx, cos is negative, right? 1 over the square root of 1 minus square whatever you have inside, which is 1 over x squared. Differentiate 1 over x squared, you get a negative 1 over, differentiate 1 over x, you get a negative 1 over x squared. Then simplify, negative, become positive. Okay, then simplify again, 1 over x squared minus 1 over x squared. So that this is the square root of x squared, the one at the bottom. If you square root it, it will be 1 over square x squared minus 1 over x, right? This and that can cancel, right? So it is 1 over x squared. Do you feel that this is very familiar? Very familiar, huh? And I told you, and then I tell you, and I also told you this one just now, right? What is the relationship between, if you have a 1 over something, how do you make it easier to differentiate? When we talk about inverse, see here, cos inverse of x over y is just secant inverse, of x, y over x. So, you know what? This is just secant inverse of x. It is 1 over, you have x outside, square root x squared come first. Finish. See, that are exactly the same. So if you see a fraction inside a inverse trigonometric function, just switch it to secant, cosecant, or cotangent, and vice versa. Alright? Number 3, cosecant inverse. But this only you have no choice but to do the chain rule. So dy dx, 1 over, is a negative, start with c, right? Start with c, so it's a negative 1 over, copy this one, square root, copy this one, square, minus 1, differentiate inside, simplify. Actually, there is not much you can do, I think. Should I expand this? I think I should. Okay, x to the 4th plus 2x plus 1 minus 1, 2x squared, sorry, my handwriting is too, let's see here, plus 1 squared. Okay, this 1 and negative 1 can cancel, and negative 2x, x squared plus 1, I can factor out x squared from x to the 4th and x squared, 2x squared, and after I take square root, it will just be x squared plus 2. This and that can cancel, negative 2, x squared plus 1, x squared plus 2. Okay, cotangent, then you have a square root, no choice, huh? Chain rule, dy dt, start with c, so it is a negative, cotangent, without square root, 1 plus whatever you have here, square, right? Then differentiate this inside function, 1 over 2t t minus 1. Differentiate this, just 1. Okay? Then simplify. Negative 1 over 2 times sec t minus 1. This and that can cancel, times t. And rearrange it nicely. T minus 1, finish. Okay? You see, it's actually very easy with the help of chain rule. Next, we have ln and we have tangent inverse. Don't worry. For ln, 1 over copy whatever inside, then differentiate inside, minus product rule here, right? Copy first function, differentiate tangent inverse. Tangent it is no square root, 1 plus square whatever inside here, then differentiate inside function, then product rule, remember, tangent inverse, copy this one, times differentiate x equal to 1, then simplify, minus how should I simplify this? I think I can see something. Multiply both top and bottom by 4 and you'll see y later. 2x, right? Over 4 plus x squared. Negative plus tangent inverse. Because this and that can cancel now, you can see it, and the answer will just be negative arctangent of x over 2, finish. Very nice. Next, okay, we have hyperbolic inverse. Sin, remember, sin it is with square root, start with 1, is a plus. Okay, so dy dx is 1 over square root of, start with 1 plus square this one, 1 over 1 plus x. Am I right? No, I'm missing out something. I forgot to do the chain rule. So I should multiply by this one times 1 again, right? Because of chain rule. Actually, it doesn't matter because you just put okay, maybe okay. Just 1 over 2 x, no x, 1 plus x, x plus x squared, finish. So always remember your chain rule, yeah? Always you need to remember to do your chain rule. Okay? Then the next one, tangent hyperbolic and product rule. Okay? dy d theta, copy first function, differentiate this. Tangent hyperbolic it is 1 over, without square root, start with 1, then minus. Okay, see, I don't even need a table, I can remember, not memorize, you just remember the pattern. Okay, then product rule, yeah? Copy, then differentiate. Okay, then simplify, and I think there is not much you can simplify. You better expand this one. Be careful with the brackets. Yeah, nothing you can simplify here, so just rearrange it. Okay, negative 1, positive 1. It's a negative, yeah? You make sure you know this is negative. So after you cancel, you have a negative 1 plus this one. Okay, finish. So it's about how you get used to the table, how you utilize the differentiation rules that you learned in the last lesson. Okay, so all these are about practicing, and you need to do a lot of exercises to get used to this. Okay, ln, you know that it is 1 over x plus product rule again, x squared, differentiate secant hyperbolic inverse, negative with x, square root. I think it starts with 1, if not mistaken. Second, yeah, 1 minus x squared. 1 minus x squared. Let's copy. Differentiate. Chain rule. Okay. Time to simplify. This and that can cancel. Positive 1 over x, negative 1 over x. 2 and 2 cancel. So, negative x secant hyperbolic inverse of x. 1 minus x squared, finish. Okay. Number 9. Now we have exponent here. dy d theta will be cosecant hyperbolic inverse. Not sure, but I think got a negative lah, because it is the last 3, right? Negative. Okay, this one, right? 1 plus with a square root. 1 over copy 1 plus 2 theta square. Remember, you need to differentiate the inside function because of chain rule. This one will just be, it's actually another chain rule lah, or you need to change it to base E, but no need lah, you know that it is 2 theta ln 2 after you differentiate. So this one cancel. Negative ln 2 over square root of 1 plus 2 square is 4 theta. And that's it. Last one. Shine, then you have a tangent inside, so obviously you need to do chain rule again. dy dx is, shine is 1 over square root, start with 1, it is plus, because of, for sine inverse it is negative, for shine inverse it is positive. Square whatever you have inside, differentiate whatever you have inside, and you know what? This is actually your identity, right? 1 plus tangent square. 1 plus tangent square, this one is secant square. So secant square x. Secant square x. This and that can cancel, the entire thing can cancel, so it is secant x, and that's it. Alright, so this is all for the derivative for inverse function. Alright, it's all about exercise. You need to do a lot of exercise to get used to the formulas, to get used to the table and the differentiation rules. The next lesson I'm going to talk about some differentiation technique, because not all the time you can differentiate like what you did in the last lesson and this lesson. Okay, sometimes you need to do implicit differentiation, parametric, and also logarithmic differentiation. Okay, so this is what we will talk about in the next lesson. So that's all for today. See you guys in the next class.